Peace, and welcome. This is the second section of Chapter 7, Hamilton's Principle. Minimal principles in physics, where nature minimizes certain important quantities like action or potential energy when a physical process takes place, have a long and interesting history. It was first developed in optics, by the assertion that a light ray that travels from one point to the other by a reflection of a plane mirror always takes the shortest possible path. But that assertion didn't yield the correct law of refraction, so it was reformulated by postulating that a light ray always travels from one point to another by the path that requires the least time. Maupertuis's principle of least action was the first application of minimum principle in mechanics. It asserts that dynamical motion takes place with minimum action. Instead of thinking of movement in terms of time, Maupertuis's principle redirects the focus on the shape of the path itself, regardless of time. But hold on a second, what do we mean by action? We can think of action as the history of a physical system. It describes its evolution over time. Mathematically, action is a scalar quantity. It's the integral of the Lagrangian, the kinetic minus the potential energy over time. Maupertuis's principle of least action was initially based on theological grounds, so it was rather vague. Only later a firm mathematical foundation was given by Lagrange. Later, Gauss developed his principle of least constraint, which was modified by Hertz's principle of least curvature. This is too many principles, right? Well, Hamilton's principle is the general formulation of all these principles. Hamilton's principle may be stated as: of all possible paths along which a dynamical system may move from one point to another within a specific time interval, consistent with any constraints, the actual path followed is the path which minimizes the time integral of the difference between the kinetic and potential energies. Let's take a look at the variational representation of Hamilton's principle. The Kronecker delta describes variation, which was discussed in the previous chapter, Chapter 6. Maybe I'll explain it too someday. The integral is required to be an extremum, not necessarily a minimum, but the minimum condition occurs almost in any important application anyways. Let's consider a particle that's fixed in rectangular coordinates. Its kinetic energy is going to be a function of only x sub I dot. And if the particle moves in a conservative force field, the potential energy will be a function of only x sub I. X sub I dot here is the first-time derivative of the position, which is velocity. And because kinetic energy equals 1/2 mv squared, kinetic energy is a function of x dot. And for potential energy, it's position energy, so it's a function of x. So T equals T, x sub I dot, and U equals U x sub I. The difference between them is L. And that means we can write L as L x sub I, x dot sub I. Let's slide it in here. And that, according to Chapter 6, can be written as this. Now, let's do some transformations. From x to t. From y sub I of x to x sub I of t. from y prime sub I of x to x dot sub I of t. And finally from f of y sub I of x, y prime sub I of x, x to L of x sub I, x dot sub I. And from chapter 6 as well, Euler-Lagrange equation is as follows. And by applying it on L, the Lagrangian, we get the following, which is Lagrange equations of motion. Now, my favorite part. Let's take an example. Let's obtain the Lagrange equation of motion of a one-dimensional harmonic oscillator.